Right now, the fastest object humans have ever built is falling toward the Sun at 692,000 kilometers per hour. That's nearly 200 kilometers every single second. It sounds like enough to escape anything, but if you pointed it at the nearest star and let it fly, you would need 6 to 500 years to arrive. 6,500 years. And that is our fastest. That is the real ceiling of what we have built. The question tonight is not whether we can do better. The question is how much better, and what the word lifetime even means once physics gets involved. Tonight we follow the physics through chemical rockets that fall short by thousands of years, nuclear engines that were actually built and then cancelled, a fusion spacecraft design that puts multiple star systems in range, and a loophole in space-time itself that changes what a human lifetime can mean. We begin. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's get one thing clear before we go any further. This is not a video about warp drives. It's not about folding space, or wormholes, or any technology that lives only inside a physics thought experiment with no engineering roadmap attached. If you came here expecting that, I want to redirect you gently but clearly, because the real answer is stranger and more interesting than any of that. Tonight, we are only talking about propulsion systems that pass through one of three filters. Either they have been built and tested, or they have been designed in serious engineering detail on paper by actual aerospace engineers with real numbers and real physics, or they follow from laws of nature we have already confirmed in laboratories. That's the rule. Everything that doesn't pass that filter stays outside tonight. No Alcubierre drives, no exotic matter, no faster-than-light anything. The known laws of physics, as best we understand them today, indicate those doors are closed, and I'm not going to pretend otherwise just to make the answer feel bigger than it is, because here is the truth. The real answer, built entirely from real physics and real engineering, is already astonishing. You don't need to exaggerate it. But before we can answer how far, we need to agree on something more basic. We need to agree on what the question actually means. And one human lifetime sounds like a simple unit until you start pulling on it. The average human being lives roughly 80 years. The first 20 of those are childhood and adolescence. The last 10 or so, depending on individual health, may not be years in which a person is in peak physical condition for deep space travel. So a realistic working travel window, the years during which an astronaut might actually be aboard a spacecraft, physically capable, mentally alert, doing the job, is roughly age 20 to age 70. That gives us 50 years. 50 years is our unit of measurement for tonight. But now here is what makes this question so much more interesting than it first appears. That 50-year unit does not always mean the same thing. At low speeds, the speeds of all current spacecraft, 50 years aboard a ship is 50 years everywhere. The clocks on the ship and the clocks on Earth stay essentially synchronized. What you experience and what Earth experiences are the same duration, but as you push toward a significant fraction of the speed of light, something happens. Not something mechanical, not something that malfunctions, something fundamental in the fabric of physics itself. Time starts passing at different rates depending on the speed of the observer. The traveler's 50 years stop matching the 50 years that pass back on Earth. The traveler ages 50 years. Earth might age 500. Or 5,000. Or in the extreme case, more than 100,000. This is called time dilation. It is not a science fiction concept. It is confirmed physics, tested in laboratories and built into the infrastructure of modern technology. We will spend significant time on it later tonight because it is the thing that changes the answer most dramatically. For now, the 50-year ruler exists, and it means different things depending on how fast you're going. The escalation tonight has 6 rungs. Chemical rockets, what we have now, what has flown, what has gotten humans to the moon. Ion drives, the efficient electric propulsion system that has sent robotic probes to asteroids and dwarf planets. Nuclear thermal propulsion, an engine concept that was actually built and ground-tested half a century ago and is being revived today. Nuclear pulse propulsion, possibly the most audacious serious engineering proposal in the history of rocketry. Fusion propulsion, the most promising concept for actually reaching another star within a human lifetime. And then, separate from all propulsion systems, the physics of near light-speed travel, where time dilation redefines what a lifetime can accomplish. Each rung on that ladder changes the answer to tonight's question. Some changes are modest. One is so large that it breaks intuition. We start at the bottom where we are right now. Chemical rockets got us to the moon. They launched every probe we have ever sent to the outer solar system. Voyager 1, New Horizons, Pioneer 10. Every spacecraft that has ever left the vicinity of Earth used chemical propulsion to break free of gravity. This is what we have mastered. 6 decades of refinement, from the V2 rocket of World War II to the space launch system flying today. And so it seems fair to start here. What is the honest ceiling of chemical propulsion, pushed to its absolute limit, when you ask it to carry a human being as far as possible in one lifetime? The answer is humbling. And to understand why, we need to spend some time with a man most people have never heard of, who wrote down the most important equation in the history of rocketry in 1903, the same year the Wright brothers first flew. Konstantin Tsiolkovsky was a Russian schoolteacher who worked at a provincial school in Kaluga, a small city about 200 kilometers from Moscow. He was largely self-educated. He had been deaf since childhood following a case of scarlet fever, which isolated him socially and pushed him toward books and independent thinking. He corresponded with other scientists but remained largely unknown during much of his working life. He died in 1935, just as the rocket age was beginning, recognized but not yet fully celebrated. Tsiolkovsky's equation, which now bears his name and is sometimes called the ideal rocket equation, describes the fundamental relationship between 3 things: the mass of propellant you carry, the exhaust velocity of your engine, and the final speed your rocket can reach. It is a simple-looking equation, but it contains a truth so frustrating that every rocket engineer for the past century has had to work within its constraints. Here is what the equation says, in plain terms. To go faster, you need more fuel. But fuel is mass. More mass means you need more fuel to accelerate it. But that extra fuel is also mass, so you need more fuel to accelerate the fuel that accelerates the fuel. The relationship between fuel mass and final speed is exponential, not linear. To double your final speed, you don't double your fuel, you square your fuel. The rocket equation grows against you every time you try to push further. To make that feel like something real, try this. Imagine you're building a car that must carry all the fuel it will ever burn, for the entire journey from the very first moment. The tank is part of the car's weight. The heavier the car, the more fuel it burns. So more fuel makes the car heavier, which makes it burn faster, which means you need even more fuel, which makes it heavier still. You cannot escape this loop. The more ambitious your journey, the more the loop tightens. That is precisely the trap that every chemical rocket is in. It isn't a question of engineering cleverness. A better nozzle won't fix it. Higher quality propellant won't fix it. The problem is structural. It's baked into the mathematics of reaction propulsion. You are always burning fuel to carry fuel. The physical ceiling on chemical exhaust velocity, the speed at which burned gases exit the nozzle, is roughly 4 to 4.5 kilometers per second. Liquid hydrogen and liquid oxygen, the most energetic chemical propellants available, have been refined over decades, and we are now close to the thermodynamic ceiling of what chemistry can produce. Combustion, no matter how efficient, cannot produce exhaust faster than its molecular bonds allow. The fastest chemically propelled spacecraft ever launched was New Horizons, which flew past Pluto in 2015. At launch, using a powerful Atlas V rocket, augmented by an upper stage and a gravity assist from Jupiter, it reached roughly 58,000 kilometers per hour, about 16 kilometers per second. That is genuinely fast. Fast enough to cross the continental United States coast to coast in about 3.5 minutes. In 50 years at that speed, New Horizons would cover roughly 25 billion kilometers. That sounds like a very large number. It is by any human scale of reference. But Proxima Centauri, the nearest star to our Sun, is approximately 40 trillion kilometers away. Not billion. Trillion. The ratio between where you'd be after 50 years at New Horizons speed and the distance to the nearest star is about 1600 to 1/10 to 1. At New Horizons' departure speed, the nearest star would take roughly 80,000 years to reach, not 50, 80,000. The Parker Solar Probe, the record holder for fastest object ever built, reaches its peak speed of 692,000 kilometers per hour, not from its engine, but from gravity. It swings close to the Sun, which accelerates it under gravitational attraction, then carries that speed outward. This technique is called a gravity assist, and it's one of the most elegant tricks in orbital mechanics. You essentially steal velocity from a planet or star's own motion around the solar system and transfer it to your spacecraft. But gravity assists only work when there's something massive to swing around. In interstellar space, the vast emptiness between stars, there are no planets, no convenient gravitational wells. The Parker Solar Probe's speed is local and non-transferable. If you pointed at Alpha Centauri today, it would take something in the range of 6,000 to 7,000 years to arrive. Voyager 1 gives us the most honest, long-term picture of what chemical propulsion delivers. Launched in 1977, it has been flying for over 47 years, a duration roughly equal to a human working career. In that time, it has traveled about 24 billion kilometers. At its current speed of roughly 61,000 kilometers per hour, it would require approximately 73,000 years to reach Alpha Centauri if it were aimed that direction, which it isn't. 47 years, and it's still, in the grand scheme of interstellar distances, barely off the doorstep. There is one more thing worth noting about chemical propulsion, which is the question of acceleration. Getting a chemical rocket to high speed requires burning most of the fuel early in the mission. After that, the engine shuts down and the spacecraft coasts for years or decades at whatever speed the initial burn achieved. There's no continuous push, no gradual build-up. You burn, then you drift. The verdict for chemical propulsion is clear. In 50 years, chemical rockets get you roughly 000 to 000029320000 light years. You haven't left the solar system's gravitational sphere of influence. You haven't reached interstellar space in any meaningful sense. The nearest star requires not one lifetime, but something closer to 1,000. Chemical rockets are magnificent for what they do. They are completely inadequate for what tonight's question demands. To go further, we need to change not how much we burn, but what we burn. We need something with more energy per kilogram. That takes us to the first step up the ladder. Propulsion powered not by chemistry, but by electricity. Ion drives operate on a completely different philosophy from chemical rockets. They don't burn anything. They use electricity to accelerate charged particles, and they are among the most fuel-efficient propulsion systems ever flown in space. The concept works like this. You start with a gas, usually xenon, a heavy noble gas that's chemically inert, easy to store, and well-behaved in a spacecraft environment. You pass that xenon through an ionization chamber, where electrons are stripped from the atoms using electrical energy. This gives the xenon atoms a positive electric charge, turning them into ions. You then pass those ions through a powerful electric field that accelerates them to very high speeds, typically 30 to 80 kilometers per second, and shoot them out the back of the spacecraft. The fast-moving ions push backward. By Newton's third law, the spacecraft is pushed forward. The key advantage over chemical propulsion shows up in a quantity called specific impulse, essentially how much thrust you get per unit of propellant consumed. A chemical rocket's exhaust exits at around 4 kilometers per second. An ion drive's exhaust exits at 30 to 80 kilometers per second. That's a factor of 10 to 20 improvement in efficiency, which means, for the same mass of propellant, an ion drive can produce 10 to 20 times as much total velocity change. In Tsiolkovsky's equation, where exhaust velocity is the critical parameter, this is a genuine improvement. We know ion drives work because we have flown them. The Dawn spacecraft launched by NASA in September 2007 is the best documented example of what a real ion drive accomplishes. Dawn's mission was extraordinary by the standards of any previous solar system exploration. Fly to the asteroid Vesta in the inner asteroid belt, achieve orbit study it for over a year, then fly to the dwarf planet Ceres, a completely different body at a completely different point in its orbit, and study that too. No spacecraft in history had ever gone into orbit around two separate extraterrestrial bodies. Dawn did it because only an ion drive had the fuel efficiency to make the trajectory work. Dawn's ion engine used xenon propellant and produced a maximum thrust of about 91 millinewtons. To give you a physical sense of what 91 millinewtons of force feels like, it's approximately equal to the weight of a single standard sheet of printer paper resting on your palm. That is the force that was moving a spacecraft the size of a mid-sized car through the asteroid belt. At that thrust level, Dawn required approximately 4 days of continuous engine operation to accelerate from 0 to 60 miles per hour. A car engine does the same thing in 5 seconds. But in space, patience pays. There is no air resistance, no friction. A tiny continuous force, applied day after day for months and years, builds velocity steadily. Dawn operated its ion engines for over 2,000 days across its mission lifetime. The total accumulated velocity change was about 11 kilometres per second, comparable to some chemical rockets but using far less propellant and over a much longer operational period. The Hayabusa missions by the Japanese space agency JAXA also demonstrated ion propulsion in operational conditions, travelling to asteroid Itokawa and later to asteroid Ryugu and returning samples. These are real, working, proven systems flying in the solar system right now. So why can't we just build a bigger ion drive and use it for interstellar travel? 2 problems. Thrust and power. The thrust problem. Even a very large ion drive produces modest thrust compared to what's needed to accelerate a crewed spacecraft quickly enough to matter. To cross the distance to Proxima Centauri in a human lifetime, you need to reach a significant fraction of the speed of light. Reaching even 1% of light speed with ion propulsion requires accelerating for an extremely long time. If your acceleration is measured in millimeters per second squared, which is typical for ion drives, reaching 1% light speed takes not months but years of continuous thrust. The power problem. Ion drives need electricity to run the electric fields that accelerate the ions. Dawn used solar panels. In the inner solar system, this works. But beyond Jupiter, sunlight intensity drops to about 4% of what it is at Earth's distance. Solar panels large enough to run a high-power ion drive in deep interstellar space would need to be enormous, hectares in area. The more practical alternative for a deep space ion drive is a nuclear reactor. But a nuclear reactor adds mass, and mass returns us to the rocket equation. Now imagine the most optimistic scenario for future ion propulsion. A large nuclear-powered spacecraft with advanced ion drives running continuously for the full 50 years of travel. Even then, advanced nuclear-powered ion drives might push a spacecraft to somewhere between 0.1 and 1% of the speed of light. At 0.1% light speed, 50 years covers about 0.05 light-years. At 1%, 50 years covers 0.5 light-years. You are now, genuinely, in interstellar space. Beyond the heliopause, beyond the outer boundary of the solar wind, beyond any reasonable definition of inside our solar system. That is a real threshold. The Proxima Centauri is still 24 light-years away. Ion drives are a genuine advance. They are not the answer. The problem isn't the principle. The problem is energy density. To truly change the equation for interstellar travel, you need a power source with a fundamentally different energy density. You need to go nuclear, not nuclear electricity, but nuclear heat directly applied. In 1955, the United States Atomic Energy Commission and the Air Force launched a classified program called Project Rover. Its question was simple. Can a nuclear reactor replace the combustion chamber of a rocket engine? This is different from nuclear-powered ion drives. An ion drive uses nuclear electricity. Nuclear thermal propulsion uses nuclear heat directly. Instead of burning hydrogen and oxygen together and riding the chemical explosion, you pump liquid hydrogen through the core of a nuclear reactor, where fission reactions heat it to extreme temperatures. The superheated hydrogen then expands through a nozzle and exits at high velocity as exhaust. The physics advantage is in the temperature. Chemical combustion of hydrogen and oxygen reaches about 3,500 Kelvin at the reaction point. That's the ceiling. A nuclear reactor core, by contrast, can reach temperatures of 2,500 to 3,000 Kelvin in the fuel, and transfer that heat to the hydrogen propellant without any combustion limit. The result, exhaust velocities of roughly 8 to 9 kilometers per second, approximately twice what the best chemical engines produce. Doubling the exhaust velocity is not a minor improvement. Remember Tsiolkovsky's equation, where exhaust velocity is the critical parameter. Doubling it transforms the fuel-to-payload ratio in a way that allows much faster spacecraft for the same fuel load, or the same speed with far less propellant. Both are genuinely useful. Project Rover began building engines, not blueprints, not computer models, actual hardware. The project produced a series of test engines with names like Kiwi, Phoebus, and Pewee, tested at a site in the Nevada desert called Jackass Flats. The tests ran through the 1960s and into the early 1970s. Engines started, ran at power, were throttled, restarted, and in some cases ran for extended durations. The Phoebus 2A engine, tested in 1968, ran at 4,100 megawatts of thermal power. The successor program, NERVI, Nuclear Engine for Rocket Vehicle Application, ran from 1961 into the early 1970s and produced engines specifically designed for spaceflight. NEVORE engines were tested for accumulated durations of tens of minutes to over an hour per test. They were rated for multiple restarts. They worked. The program was cancelled in January 1973. Not because the technology failed, not because a test went wrong. It was cancelled because the Nixon administration cancelled the crewed Mars mission program that NERVA was being developed for. No Mars mission, no need for the engine. Budget cuts did what physics couldn't. This matters because it means nuclear thermal propulsion is not a concept awaiting validation. It is a technology that has been demonstrated in hardware. The knowledge exists. The engineering exists. The intellectual capital. The test data. The measured performance. All of it was generated and documented in the 1960s. What has been missing for 50 years is the will to deploy it. That may be changing. In 2023, NASA and DARPA jointly announced a program called DIRECO, Demonstration Rocket for Agile Cislunar Operations, aimed at demonstrating a nuclear thermal rocket in space by the mid-2020s. Private companies including Lockheed Martin and BWX Technologies have contracted to work on the hardware. Nuclear thermal propulsion is being actively revived. In theory, a well-designed nuclear thermal spacecraft could reach somewhere between 3 and 10% of the speed of light. In 50 years at 3% light speed, you cover about 1.5 light years. In 50 years at 5% light speed, about 2.5 light years. That's a meaningful step. You are now more than halfway to Proxima Centauri. You're solidly in interstellar space, in territory that no human and no spacecraft currently operating has ever reached. 2.5 light years is roughly 23 trillion kilometers. That is a genuinely different scale from anything chemical propulsion offers. But you haven't arrived, and there is a tax that comes with the nuclear thermal approach. A nuclear reactor on a spacecraft produces radiation, not just the heat that does useful work, but ionizing radiation that travels outward in all directions. The crew has to be shielded from this, which requires heavy shielding material placed between the reactor and the crew compartment. Heavy shielding means more mass. More mass means more propellant. The rocket equation taxes every solution. Despite these challenges, nuclear thermal propulsion represents a real, tested technology with a genuine engineering roadmap. It is not science fiction, it is something humans have already built. The gap between where we are and where it could take us is a gap of political will and funding, not fundamental physics. But to reach another star in a human lifetime, we need to go further than any thermal reactor can realistically take us. We need not just more heat, but more energy. Energy from a different source entirely. In 1958, a physicist named Freeman Dyson arrived at a small secretive project in San Diego called Project Orion. He had been recruited by an engineer named Ted Taylor, and the idea they were developing together was one of the most extraordinary things anyone has seriously proposed in the history of rocketry. What if the propulsion system was nuclear bombs? Not metaphorically, not nuclear-powered in some indirect sense. Actual nuclear warheads detonated one after another behind a spacecraft, with the shockwave and plasma from each explosion pushing against a thick metal plate called a pusher plate, attached to the front of the ship by a set of enormous shock absorbers. Each detonation would shove the plate. The shock absorbers would smooth the impulse into continuous thrust. The ship would accelerate. Wait a few seconds. Eject another warhead. Detonate. Repeat. Dyson and Taylor ran the numbers. And the numbers worked. A nuclear explosion produces exhaust plasma, moving at velocities of thousands of kilometers per second. That is hundreds of times faster than a chemical rocket's exhaust, and significantly faster than a nuclear thermal engine. In Tsiolkovsky's equation, that exhaust velocity produces a fundamentally different result. An Orion ship would not need enormous quantities of fuel per unit of velocity gained. Each bomb provides a powerful push, efficiently. The designs Orion produced ranged enormously in scale. The smallest proposed Orion spacecraft would have weighed a few hundred tons. The largest concepts, the ones Dyson found most interesting, were measured in hundreds of thousands of tons, city block-sized vehicles powered by bombs the size of small cars. For the large designs, Dyson estimated cruise speeds of roughly 3 to 10% of the speed of light. His most optimistic calculations suggested that a sufficiently large Orion ship could reach Alpha Centauri in somewhere between 40 and 130 years, depending on the design. The lower end of that range, 40 to 50 years, is one human working lifetime. Sit with that for a moment. A technology that was designed in detail by working physicists and engineers using 1950s and 1960s science could theoretically have reached the nearest star in one human lifetime. This is not a modern proposal. Dyson and Taylor were working with equations that Tsiolkovsky would have recognized. The concept extended further than Alpha Centauri. Dyson himself, in later life, wrote about what he called Orion's children, hypothetical future civilizations that might use nuclear pulse propulsion to colonize nearby star systems, carrying entire ecosystems aboard massive ships. He wasn't describing fantasy, he was extrapolating from engineering that he had personally worked on and believed in. So why doesn't one exist? On August 5, 1963, the United States, the Soviet Union, and the United Kingdom signed the Partial Nuclear Test Ban Treaty. Its purpose was to stop atmospheric nuclear testing, which was filling the global atmosphere with radioactive fallout. The treaty banned nuclear detonations in the atmosphere, underwater, and in outer space. Project Orion required detonating nuclear weapons in space, hundreds of them, every few seconds, for years. The treaty didn't specifically name Orion. It didn't have to. The moment it was signed, Orion was legally impossible. The program was cancelled the following year. There were other problems too. The original Orion designs called for launching from Earth's surface, which would have required detonating hundreds of nuclear bombs in the lower atmosphere just to reach orbit, an act of radioactive fallout so severe it would have been globally catastrophic. Later designs proposed building the ship in orbit, bypassing that problem, but by then the political moment had passed. Dyson wrote more than once in his later career that the cancellation of Project Orion was one of the genuine tragedies of the space age. He meant that not as a dramatic flourish, but as a considered judgment. The physics was sound. The engineering was challenging but tractable. What killed it was a treaty aimed at a different problem that happened to make Orion impossible as a side effect. The verdict on nuclear pulse propulsion. The physics is genuinely sound. This is the first propulsion concept on tonight's list that puts a human being within real striking distance of another star in a single lifetime, at 5 to 10% light speed. Proxima Centauri is 42 to 84 years away. At the optimistic end, one lifetime, one way, no return, but is actually happening in physicism, but is actually happening in something that isn't a fantasy. The technology is frozen in political amber. Not because it doesn't work, because of a treaty that nobody signed with rocketry in mind. The next step on the ladder doesn't use fission at all. It uses the other kind of nuclear reaction, and the difference in energy is dramatic. If you're still here, this channel was probably made for you. A quiet subscribe helps more people find their way here, and keeps these slow, careful walks through the physics of space coming. There is a distinction in nuclear physics that matters more for this question than almost anything else, and it comes down to the difference between two kinds of nuclear reactions. Fission is what nuclear power plants do. You take a heavy, unstable atom, uranium or plutonium, and break it apart. The pieces weigh slightly less than the original atom, and that missing mass is released as energy. It's powerful. The atomic bombs dropped on Hiroshima and Nagasaki were fission devices. So are all commercial nuclear power reactors operating today. Fusion is the opposite. You take light atoms, usually hydrogen or its heavier relatives, deuterium and tritium, and you force them together under extreme heat and pressure until they merge into a heavier atom. Again, the products weigh slightly less than the ingredients, and again that missing mass becomes energy. But the energy released per kilogram of fuel is roughly 10 to 100 times greater than fission, depending on the specific reaction. Fusion is what powers the sun. It is what powers every star in the visible universe. The reason stars shine is that their cores are hot and dense enough to force hydrogen atoms together continuously, releasing energy at a rate that has sustained some of them for billions of years. For propulsion, the implication is straightforward. If you can run a fusion reactor and use its exhaust to push a spacecraft, your exhaust velocity will dwarf anything fission can produce. And in Tsiolkovsky's equation, exhaust velocity is everything. In 1973, the British Interplanetary Society launched a 5-year engineering study. The goal was not to speculate about fusion propulsion in vague terms, but to design an actual spacecraft hull, engines, fuel load, staging, mission profile, and arrival scenario. They called it Project Daedalus, after the mythological craftsman who built wings of feathers and wax. The design was published in full in 1978. It was an uncrewed probe designed to reach Barnard's star, a red dwarf approximately 9 light-years from Earth, within 50 years of flight time. The engine used a process called inertial confinement fusion. Small pellets, about 1 gram each, composed of a mixture of deuterium and helium-3, would be ignited by beams of high-energy electrons, triggering a fusion reaction. The plasma produced by each ignition event would be directed by a magnetic field, which acts as a nozzle, because no physical nozzle material could survive contact with fusion plasma temperatures. The ship would fire these pellets at a rate of 250 per second in the first stage. The projected cruise speed, approximately 12% of the speed of light. At 12% light speed, Barnard's star at 5.9 light-years is reached in about 49 years. Proxima Centauri at 424 light-years is reached in about 35 years. Wolf 359 at 79 light-years takes about 65 years, slightly over 1 working lifetime. For the first time on tonight's list, the answer to how far in 1 lifetime includes multiple other star systems, not marginally, comfortably. Now the fuel problem. Daedalus burns deuterium and helium-3. Deuterium, heavy hydrogen, is extractable from seawater and is not in short supply. Helium-3 is the problem. Helium-3 is a specific isotope of helium with 2 protons and 1 neutron. On Earth, it is extraordinarily scarce. The atmosphere contains virtually none. The total global stockpile of helium-3 produced by the United States over decades of weapons maintenance is measured in kilograms. Daedalus requires roughly 30,000 metric tons of helium-3. That is not a rounding error. 30,000 tons of a substance we currently have in kilogram quantities. The Daedalus study proposed mining helium-3 from the upper atmosphere of Jupiter, where it is more abundant, using robotic balloon mining systems that would float in the Jovian atmosphere and extract helium-3 from the gas. The study estimated this would require approximately 20 years of continuous automated mining to gather sufficient fuel for 1 mission. This is not physically impossible. It is an industrial operation on a scale that no human civilization has ever attempted. Then there is the ignition question. For any fusion reactor to work, the fusion reaction must produce more energy than it costs to initiate it. For decades, no fusion device achieved this. Every attempt produced less energy out than was put in to start the reaction. In December 2022, that changed. The National Ignition Facility at Lawrence Livermore National Laboratory in California achieved fusion ignition for the first time in human history, A laser-driven fusion reaction produced 315 megajoules of energy from 2,408.05 megajoules of laser energy delivered to the target. More out than in. Net energy gain confirmed. That is a genuine scientific milestone. The gap between this laboratory result and a working fusion engine running continuously for 24 years aboard a spacecraft remains enormous. But the direction is confirmed. The verdict on fusion propulsion: it is the most physically promising concept on tonight's list. At Daedalus performance levels, multiple star systems within 6 to 10 light-years become one-lifetime destinations. The fuel problem is large but theoretically tractable. The ignition challenge is actively being addressed. Fusion propulsion isn't ready. But it is the direction that, if engineering follows physics, actually leads somewhere. There is one more concept before we reach the physics that changes the entire question, and it approaches the problem from the opposite direction, not by building a more powerful engine, but by making the spacecraft so light that even the most delicate push in the universe becomes enough. A photon, a particle of light, has no mass, but it carries momentum. And when a photon hits a reflective surface and bounces off, it transfers a tiny amount of that momentum to the surface. This is called radiation pressure. It has been understood since the 19th century and measured in laboratories for over 100 years. In everyday experience, radiation pressure is completely undetectable. The pressure of sunlight on your face on a bright day is about 9 micronewtons per square meter. It does nothing you would ever notice. But in space, with no air resistance and no friction, even a tiny force applied continuously produces acceleration. And if you build a spacecraft that is essentially just a very large, very light reflective sail, with almost no mass to accelerate, the math starts to change in interesting ways. Solar sails are not theoretical. The Japanese spacecraft Ikaros, interplanetary kitecraft accelerated by radiation of the Sun, launched in May 2010 and deployed a 40-meter square reflective sail made of polyimide film about 7.5 micrometers thick. The spacecraft's instruments confirmed that sunlight pressure was providing real, measured thrust and attitude control. It worked. The concept has been demonstrated in space. NASA's LightSail 2 mission, launched in 2019 by the Planetary Society, similarly deployed a solar sail in low Earth orbit and demonstrated controlled solar sailing. The technology is real, but solar sails powered by sunlight have a hard limitation. The intensity of sunlight falls off as the square of the distance from the Sun. At Jupiter's distance, sunlight is about 4% as intense as at Earth. For a solar sail attempting to cross full 24 light-years to Proxima Centauri, sunlight provides negligible thrust for almost the entire journey. The idea behind Breakthrough Starshot is to replace sunlight with a laser. A ground-based laser array, many individual lasers working in phase with each other, collectively producing roughly 100 gigawatts of power, would fire at a tiny spacecraft carrying an ultra-thin reflective sail. Because the laser can maintain its intensity across a much larger distance than sunlight, it can push the sail for long enough to reach a significant fraction of the speed of light. Breakthrough Starshot was announced publicly on April 12, 2016, the 55th anniversary of Yuri Gagarin's first spaceflight, by Stephen Hawking and the Russian billionaire Yuri Milner, with physicist Freeman Dyson among the advisors. The initiative was seeded with $100 million from Milner. It has a scientific advisory committee with serious researchers attached. The target for the spacecraft, which the project calls a Starship, is roughly 1 gram. A gram. The sail would be a few meters across. The 100 gigawatt laser fires for approximately 10 minutes, accelerating the Starship to about 20% of the speed of light. After that, the spacecraft coasts to its destination under no further power. At 20% light speed, Alpha Centauri is roughly 21 years away. A gram-scale probe could, in principle, transmit images of the Alpha Centauri system back to Earth within this century, if the program began in earnest today. The physics is legitimate. No new laws of nature are required. But now ask the obvious question: what about human passengers? The reason laser sails can reach 20% light speed is that the payload is 1 gram. 1 gram, a spacecraft carrying a human being with life support, crew quarters, food, water, radiation shielding, navigation, and everything else needed to keep a person alive for 21 years, weighs not 1 gram but hundreds of metric tons. To accelerate that mass to 20% light speed using laser radiation pressure, you would need something on the order of 100 million times the current global electricity production of Earth, applied continuously for the duration of acceleration. There is also the deceleration problem. A laser sail gets pushed away from Earth by the laser. When it arrives at Alpha Centauri, it is still moving at 20% light speed. There is no laser there to slow it down. A gram-scale probe can zip through the system in hours, taking photographs, and continue into deep space, which might be scientifically acceptable. A crewed spacecraft must stop. The laser sail concept has no deceleration mechanism for a human-scale mission. The verdict on laser sails, a genuine revolution in robotic exploration of nearby stars. A credible, funded, physics-consistent path to sending gram-scale probes to Alpha Centauri within this century. For human passengers, the concept does not currently scale, but Breakthrough Starshot does something important for tonight's conversation. It defines the lower edge of the relativistic regime, the speed range at which something fundamental happens to time. At 20% light speed, time dilation becomes measurable. At 50%, it becomes significant. And at 90% and above, time dilation becomes the most important variable in the entire problem of how far a human being can travel in one lifetime. That is what we need to understand now. Everything we've discussed so far rests on an assumption so natural, it barely feels like an assumption. We have been treating 50 years as 50 years everywhere. Time on the ship passes at the same rate as time on Earth. The clocks stay synchronized. They don't. This is not a figure of speech. It is not a philosophical statement about perception. It is a measured, confirmed, experimentally replicated fact about the physical structure of the universe we live in. Time passes at different rates for objects moving at different speeds. The faster you move through space, the slower you move through time, relative to an observer who is stationary. Albert Einstein laid out the mathematics of this in his special theory of relativity, published in 1905, but a theory in 1905 is just a theory. The question is whether the universe actually works that way, and the answer, confirmed by dozens of independent experiments over the past century, is yes, completely. The most direct early tests came in 1971 when physicists Joseph Hafele and Richard Keating carried cesium atomic clocks aboard commercial airliners and flew them around the world eastward and then westward, comparing the flying clocks to reference clocks that stayed at the U.S. Naval Observatory in Washington. When the flights returned, the clocks that had traveled showed time differences, to within the measurement precision of the instruments, exactly what Einstein's equations predicted. Time had passed at slightly different rates for the flying clocks and the stationary clocks. The experiment has been repeated multiple times since with increasing precision, always confirming the relativistic prediction. In 1976, a NASA rocket experiment called Gravity Probe A launched a precision hydrogen maser clock to an altitude of about 10,000 kilometers and compared it to a ground-based clock. The time rate difference matched the combined gravitational and velocity effects predicted by general and special relativity, to a precision of about 70 parts per million. The universe was behaving exactly as Einstein said it would. Today, the global positioning system depends on this physics to function. GPS satellites orbit Earth at roughly 14,000 kilometers altitude and move at about 14,000 kilometers per hour relative to the ground. Relativity predicts that their onboard clocks run at a slightly different rate than clocks on Earth. The net effect is that satellite clocks gain roughly 38 microseconds per day relative to clocks on the ground. That's small, but if the GPS system didn't correct for it, the satellite positions would accumulate error at a rate of roughly 10 kilometers per day. Your navigation app would be pointing you to the wrong city within a week. Relativity is not abstract. It is in the software that tells you where to turn. Sit with that for a moment. The same equation Einstein wrote in 1905 is what keeps your maps accurate today. The mathematical quantity that describes how much time slows at a given speed is called the Lorentz factor, named after the Dutch physicist Hendrik Lorentz, who derived it before Einstein incorporated it into the full relativistic framework. At low speeds, the Lorentz factor is very close to 1. meaning time is passing at almost the same rate for the traveler and the observer. But as speed approaches the speed of light, the Lorentz factor grows rapidly. At 99% of light speed, it is about 7. At 99.9%, it is about 22. At 99.99%, about 71. The closer you get to light speed, the more dramatically time slows for the traveler. Let me put specific numbers in front of you, because this is where the question changes. At 10% light speed, for every 100 years that pass on Earth, the traveler ages about 99. 5 years. The difference is real but small. At 50% light speed, for every 100 Earth years, the traveler ages about 87 years. Measurable and meaningful. At 90% light speed, for every 100 Earth years, the traveler ages about 44 years. The traveler ages about 44 years. The traveler is aging at less than half the rate of Earth-based observers. At 99% light speed, for every 100 Earth years, the traveler ages about 14 years, 7 times slower aging than Earth. At 99 slower aging than Earth. At 99.9% light speed, for every 100 Earth years, the traveler ages about 4-5 years. Earth is aging 22 times faster than the traveler. There is a lot to absorb there. Take a breath before we go further. Now you see the loophole. If you can travel fast enough, the universe's geometry works in your favor. You experience 50 years of biological aging, but the distance you cover in those 50 subjective years is not limited to 50 light years. It can be hundreds, thousands, because from the universe's perspective, you have been in transit for much longer than your body has registered. The universe doesn't care about your biological clock. It has its own geometry, and that geometry allows enormous distances to be crossed in a single human lifetime of subjective time. This is not a trick. No law of physics is being bent. The universe simply works this way. The most instructive scenario for thinking about this is the constant 1G acceleration mission, a spacecraft that maintains a continuous acceleration of exactly 1G. This is the pull of Earth's gravity felt at the surface. The force you feel sitting in a chair right now. Not violent, not physically taxing. Just the steady, familiar weight that humans have evolved to live under. At 1G constant acceleration, you reach 10% of light speed after about 35 days, 50% after about 200 days, 90% after about a year and a half, 99% after about a year and a half, 99% after about 3 years. Your speed is asymptotically approaching but never quite reaching the speed of light. As you accelerate, the Lorentz factor climbs, and time on the ship slows further and further relative to time outside. Here is what this produces in ship time for various destinations. You leave Earth at age 20, accelerating at 1G toward the target, flipping at the midpoint and decelerating at 1G to arrive at rest. Alpha Centauri at 24 light years, about 3-6 years of ship time. You land at age 23. 6. Earth has experienced about 5-9 years. The people you knew are slightly older. Communication has a growing delay but is still possible. This is, in terms of human experience, manageable. The center of the Milky Way at roughly 26,000 light years, about 20 to 21 years of ship time. You arrive in your early 40s. Earth has experienced roughly 26,000 years, 260 centuries. Every civilization that existed when you left is long dead. Every language has changed. Every nation has risen and fallen multiple times over. Andromeda Galaxy at about 25 million light years, approximately 28 years of ship time. You are 48 years old when you arrive. Earth has experienced 5 million years. Hold that picture for a moment before we go further. You, 48 years old. Earth, 5 million years older. The universe allows this. In 50 active years of ship time at 1G, starting from age 20 and ending at age 70, you could travel to destinations tens of thousands of light years away and still arrive in middle age. The Milky Way, 100,000 light years in diameter, could theoretically be crossed in roughly 25 years of ship time at 1G. The physics permits this. No equation is violated. No law is broken. The universe does not forbid it, but the energy cost is staggering. To accelerate 100 metric tons at 1 g to near light speed and then decelerate symmetrically at the destination requires converting an amount of matter into pure energy that is many times the mass of the vehicle itself. The most efficient conceivable fuel is matter-antimatter annihilation, which converts mass to energy at 100% efficiency. Even with perfect antimatter propulsion, the quantity of antimatter needed to carry a 100-ton ship to 99% of light speed runs to tens of thousands of metric tons. The entire world output of antimatter from all particle physics laboratories combined amounts to about 10 nanograms per year. The gap between that and the required fuel load is not an engineering gap. It is a civilization scale gap, and yet the physics allows it. The universe doesn't say no. It only says the energy must come from somewhere. Not yet is a different answer from never. Let's grant a generous assumption. Let's say fusion propulsion achieves Daedalus-level performance. A spacecraft is underway. 12% light speed. Destination Alpha Centauri. Arrival 35 years from now. The fuel burns. The physics holds. The ship works. What is happening to the people inside? This is not a secondary question. It is, in many ways, the defining engineering challenge of crewed interstellar travel, and it has multiple distinct, serious components that are worth understanding carefully. The first problem is radiation. Space is not empty. The volume between stars is permeated by cosmic rays, high-energy charged particles produced by some of the most violent events in the universe: supernova explosions, collisions between neutron stars, active galactic nuclei. These particles travel at close to the speed of light and carry enormous amounts of energy. Most of them are protons. Some are heavier nuclei. All of them are capable of damaging biological tissue and DNA when they pass through it. On Earth's surface, we are protected from this by two overlapping shields. The planet's magnetic field deflects the charged particles that would otherwise stream down into the atmosphere, and the atmosphere itself, roughly equivalent in shielding mass to 10 meters of water, absorbs much of what gets through. Cosmic ray exposure at Earth's surface is roughly 0.3 millisieverts per year, negligible by any safety standard. In low Earth orbit, aboard the International Space Station at 400 kilometers altitude, astronauts sit just inside the outer edge of Earth's magnetic protection. Their annual radiation dose is roughly 100 to 150 millisieverts, 300 to 500 times higher than on the ground. Elevated, but within acceptable limits for career astronauts who are monitored carefully. In deep interplanetary space, during a Mars transit, there is no magnetic field protection. NASA estimates that Mars mission astronauts would receive roughly 0 to 0.6 sieverts of radiation during the roughly 9-month transit each way. That's approaching the career dose limit for US radiation workers in a single transit. The return trip doubles it. A mission lasting 35 years in deep interstellar space would accumulate radiation exposure that with current shielding technology would almost certainly exceed safe lifetime limits by a significant margin. Water is one of the better radiation shields for the specific particles involved in galactic cosmic rays, because its hydrogen content absorbs energy through elastic collisions in a way that heavy metals do not. Some mission designs surround crew compartments with tanks of water, providing shielding while also serving as the water supply. Superconducting magnetic deflection coils creating a miniature version of Earth's own magnetic field around the ship are another concept. Neither is worked out to a practical engineering design for a multi-decade mission. Both add mass. We will come back to what that mass cost means in a moment. The second problem is gravity. The human body has spent hundreds of millions of years, not just its evolutionary history as a species, but its entire lineage back through vertebrate life under continuous gravitational pull of approximately 1 g. The cardiovascular system evolved to pump blood upward against gravity. The bones evolved to bear a load proportional to body weight. The vestibular system evolved to detect orientation relative to gravitational down. The entire physiology assumes gravity exists and acts consistently. Remove gravity, and the body begins adapting in ways that are harmful over long periods. Bone density decreases at roughly 1 to 2% per month in microgravity, not because anything is breaking, but because the body interprets the absence of gravitational load as a signal that the bones are over-engineered and reduces their mass to save resources. Over a 35-year mission in zero gravity, this would produce skeletal fragility that cannot be reversed. Muscle mass decreases similarly. The heart, which no longer needs to work against gravity to push blood to the head, gradually weakens. Body fluids shift upward toward the head and chest, because gravity is no longer pulling them toward the legs. This fluid shift increases intracranial pressure, which many astronauts experience as a persistent headache and blurred vision. The syndrome has its own clinical name, Spaceflight-Associated Neuroocular Syndrome, or SANS. It has been documented in a substantial proportion of astronauts who spend 6 months or more aboard the ISS. Sit with that number for a moment. 6 months. On an interstellar mission, there is no rehabilitation. The mission is the rest of your life. The engineering solution is artificial gravity, spinning a section of the spacecraft so that centrifugal force substitutes for gravitational pull. The physics is completely understood. A person standing on the rim of a rotating cylinder experiences a centrifugal force directed outward from the axis of rotation. If the rotation rate and the radius of the cylinder are chosen correctly, this force is indistinguishable from gravity in its effect on the body. The design constraint is that the rotation rate must be low enough that humans don't experience motion sickness from the Coriolis effect. Most research suggests that rotation rates below about 2 revolutions per minute are tolerable for most people. At 2 rpm, the habitat radius needed to generate 1 G at the rim is about 225 meters. That is a very large structure to build, launch, and maintain in space. The third problem is time and isolation. Humans are social animals. We evolved in groups of 50 to 200 individuals with constant interaction, shifting relationships, access to a broader community, and the ability to leave a group that was dysfunctional. Our psychology is built around the assumption of social access. We are not evolved for prolonged, inescapable isolation in a small group with no outside contact. The best data we have on prolonged isolation comes from Antarctic research stations. The Concordia station, operated jointly by France and Italy on the Antarctic plateau, maintains a crew of about 13 people through the winter season. Roughly 9 months during which weather makes evacuation impossible, and outside contact is limited to radio and satellite communications. Researchers at Concordia and similar stations consistently document psychological effects including increased irritability, interpersonal conflicts, depression, cognitive changes, and what is called third quarter phenomenon. A measurable drop in psychological well-being when the crew realizes they are past halfway but still far from home. These effects occur in highly trained, carefully selected professionals. Over 9 months, a crewed mission to Alpha Centauri at fusion propulsion speeds takes 35 years. Over that time, the crew would spend their entire professional adult lives in an enclosed metal structure, unable to add or remove members, unable to leave, with communication delays to Earth growing from months to years as the ship proceeds. By the time the ship is halfway to Alpha Centauri, a message to Earth takes over 2 years to arrive and another 2 years for a reply. There is no real-time support, no option to turn around. Crew selection, training, mission design, psychological support tools, and possibly pharmacological assistance can all help. How much they can help over timescales and conditions that have never been studied is genuinely unknown. None of these problems make interstellar crewed travel physically impossible. They are solvable, in principle, with engineering investment and research. But each solution adds mass, cost, complexity, and risk. And on a mission where the nearest assistance is measured in light years and years of communication delay, every unresolved risk is a potential catastrophe with no recovery option. The human body is not the reason a crewed interstellar mission cannot happen. It is one more real, serious constraint that compounds every other constraint. The ship is not the only thing that has to survive the journey. Let's take stock before the landing. Chemical rockets at peak performance get you 003 to 03.0032 light-years in a lifetime. You remain inside our solar system. No star is reached. The nearest star requires not 50 years, but tens of thousands. Advanced ion drives with nuclear power sources push the boundary to roughly 0.05 to 0.05 to 0.5 light-years in a lifetime. You have crossed the heliopause and entered true interstellar space, but the nearest star ahead of you still represents years of further travel at speeds you cannot achieve. Nuclear thermal propulsion at its theoretical ceiling gives you 1.5 to 2.5 light-years in a lifetime. You are past halfway to Proxima Centauri for the first time on this list, solidly in interstellar space at distances no human probe has ever reached. Nuclear pulse propulsion at Project Orion design performance puts you at 2.5 to 5 light-years in a lifetime. At the optimistic end, Proxima Centauri is within reach. One way, no return, but actual arrival at another star system becomes something the physics permits. Fusion propulsion at Daedalus level performance covers 6 light-years in 50 years. Not just Proxima Centauri, but Barnard's star, Wolf 359, and several others. Multiple nearby star systems become genuine one-lifetime destinations. The question changes from, can we reach a star, to, which star? Laser cell probes at breakthrough starshot target speeds cover 10 light-years in 50 years for robotic probes of 1 gram. For humans, the concept does not currently scale, and then the physics itself, independent of any specific propulsion technology. At 99% light speed, time dilation means 50 years of biological aging corresponds to roughly 350 light-years of actual travel. At 1 g continuous acceleration, a 50-year ship-time journey covers tens of thousands of light-years. The Milky Way diameter fits within one human's subjective lifetime. The energy to achieve this, currently beyond any engineering roadmap by orders of magnitude. The physics, completely consistent with everything we know about the universe. That is the honest range, from 0.02032 light-years to tens of thousands, depending on where you draw the line. Let's come back to where we began. The Parker Solar Probe, the fastest object humanity has ever constructed, is moving right now at 692,000 kilometers per hour. That number opened tonight's conversation. Let's close with it. Every number we walked through tonight, except the relativistic extreme, involves propulsion that either already exists or has been designed in real detail. Chemical rockets, 1960s technology, flying today. Nuclear thermal, ground-tested in Nevada in the 1960s. Being revived now. Nuclear pulse, engineered in detail by Freeman Dyson and Ted Taylor in 1958. Fusion propulsion, designed in full engineering detail by the British Interplanetary Society in 1978. The time dilation physics, confirmed by experiments since 1971, running in GPS satellites today. The gap between where we are and the stars is not a gap in understanding. The physics is known. The equations are written. The path from where we stand to one of these propulsion systems takes a human to another star is a path of engineering, energy, and political will. Those are real gaps. They are large, in some cases enormous, but they are different in kind from the universe doesn't allow it. The universe allows it. The Parker Solar Probe is doing 692,000 kilometers per hour right now. This moment, falling toward the sun, the fastest thing we have ever made. And it would still need 6,500 years to reach the nearest star. Somewhere between that number and the far edge of the Milky Way, the honest answer to tonight's question lives. We know where the floor is. We can see, at least in outline, where the ceiling might be. And the ceiling, it turns out, is not where most people thought to look for it. Thank you for spending this time here. If tonight settled something for you, a like or subscribe helps this channel reach more people who need exactly this kind of quiet evening. It means a great deal. The universe is patient.